Tuning model complexity, Bias-Variance Dilemma. Let us say that a sample x, which is equal to set x to the t or to the t, is drawn from some unknown joint probability density p of xr. Using this sample, we construct our estimate g dot. The expected square error over the joint density at x can be written as, using the equation 4.17, we get 4.35, that the expectations of r minus g of x to the square conditioning on x is equals to the expectations of r minus the expectations of r conditioning on x to the square conditioning on x plus the expectations of r conditioning on x minus g of x to the square. So the first term is called noise. The second term is called squared error. The first term on the right is the variance of r given x. It does not depend on g dot or x. It is the variance of noise added rho square. This is the part of error that can never be removed, no matter what estimator we use. The second term quantifies how much g dot g of x deviates from the regression function, the expectations of r conditioning on x. So this does depend on the estimator and the training set. It may be the case that for one example, g of x may be a very good fit, and for some other example, it may make a bad fit. To quantify how well an estimated g dot is, we average over possible data sets. The expected value, average over samples x, all of size n and drawn from the same joint density, p of rx, is, using equation 4.11, 4.36, ex, the expectation x of expectations of r conditioning on x minus g of x to the square, then conditioning on x is equals to the square of the expectations of r conditioning on x minus ex of g of x. Then the difference of this to the square, we call it bias, plus the next term, because we minus the expectation ex of g of x to the square. Now the next term is the ex of the expectations of gx minus ex of g of x, then to the square. Then we take the ex expectations of x. We call this the variance. So as we discussed before, bias measures how much g of x is wrong disregarding the effect of varying samples, and variance measures how much g of x fluctuate around the expected value. Expectation of g of x as the sample varies. We want both to be small. So let us see a didactic example. To estimate the bias and the variance, we generate a number of datasets xi equals to the xi to the t, ri to the t, and I starting from 1 to 3 until m from some known f dot function with added noise, using each dataset to form an estimated gi of dot and calculate the bias and the variance. Note that in real life we cannot do this because we do not know f dot or the parameters of the added noise. Then the expectations of g of x is estimated by the average over gi dot. That is, g bar of x is equals to 1 over m times the summations of gi of x, summing with index I starting from 1 to m. Estimated bias and variance are bias square of g is equals to 1 over n times the summations summing for all index t of the following term, which is the square of the difference of g bar of x to the t minus f of x to the t. And the variance of g is equals to 1 over n times m times the doubling summation with outer summation summing for all index t and inner summation summing for all index I of the square of the following terms is the difference between gi of x to the t minus g bar of x to the t. Now let us see some models of different complexity. The simplest is a constant fit, gi of x is equal to 2. This has no variance because we do not use the data and all gi of x are the same. But the bias is high unless, of course, f of x is close to 2 for all x. If we take the average of r to the t in the sample, gi of x is equal to the summations of ri to the t over n, and summing for index t, instead of the constant 2, this decreases the bias because we would expect the average in general to be a better estimate. But this increases the variance because the different samples xi would have different average values. Normally, in this case, the decrease in bias would be larger than increase in variance, and the error would decrease. Okay, in figure 4.5, a is a function f of x which is equals to 2 times sine of 1.5x and one noisy, the normal distribution of 0, 1 dataset sampled from the function. 5 samples are taken, each containing 20 instances. That is, B, C, D are 5 polynomial fits, namely gi dot of order 1, order 3, and order 5. For each case, dotted line is the average of the 5 fits, namely g bar of dot. So in the context of polynomial regression, an example is given in figure 4.5. As the order of the polynomial increases, small changes in the dataset cause a greater change in the fitted polynomials, thus variance increases. But a complex model on the average allows a better fit to the underlying function, thus bias decreases. See figure 406. This is called the Bias-Variance Dilemma, and is true for any machine learning system and not only for polynomial regression. Giemann, Bienenstock, and Dorr-Red, 1992. To decrease bias, the model should be flexible at the risk of having high variance. If the variance is kept low, we may not be able to make a good fit to data and have high bias. The optimal model is the one that has the best trade-off between the bias and the variance. If there is a bias, this indicates that our model class does not contain the solution. This is underfitting. If there is variance, the model class is too general and also learns to the noise. This is overfitting. If g dot is of the same hypothesis, class with f dot, for example, a polynomial of the same order, we have an unbiased estimator, and the estimated bias decreases as the number of models increase. This shows the error-reducing effect of choosing the right model, which we called inductive bias in chapter 2. The two uses of bias are different but not unrelated. As for variance, it also depends on the size of the training set. The variability due to sample decreases as the sample size increases. To sum up, to get a small value of error, we should have the proper inductive bias. To get small bias in the statistical sense and have a large enough dataset so that the variability of the model can be constrained with the data. Note that when the variance is large, bias is low. This indicates that g bar of x is a good estimator. So to get a small value of error, we can take a large number of high variance models and use their average as our estimator. We will discuss such approaches for model combination in chapter 17.